Hey there, here we go into lesson 6, polar differentiation. In other words, we're going to be taking derivatives of polar equations, but not in the way that you might at first think. We're going to be going back and basically making things into parametric equations first, and then dealing with everything like you've seen it before. What the heck do I mean? Well, let's see. So when we differentiate polar functions, we're sometimes going to just straight up take the derivative. Just find r prime of theta or dr d theta. But many other times, we're going to first rewrite r equals a function of theta. So just call r some polar function in terms of theta. And we need to recall that that ends up equaling to, well, f of theta, or I'll just kind of write it as r, cosine of theta, which is the same as saying taking whatever that function of theta is and multiplying it by cosine theta. So we'll do that in a little bit. And then to find the y coordinate of any polar function, we would take r sine theta. And this comes from our, well, understanding of translating from polar to rectangular form. And if you haven't seen that before, look back at an earlier lesson. That'd be lesson 4 to check that out. So those conversions for the y value would be f of theta, sine of theta. And more on that in a little bit, but these conversions are going to help us tremendously to basically be able to do what we've done before. So x and y act independently of each other in terms of theta now by taking that step. And essentially what we've just done is we've made a polar function into a set of parametric equations where the x value is determined by r cosine theta and the y value is determined by r sine theta. It's awesome. All right. So a lot of old stuff in here and a lot of algebra, some trig too, but don't worry about it. It's not as bad as the length of the problem might look. You'll see what I mean. So we're told to write r equals sine of 2 theta as a set of parametric equations in terms of theta. This is just a drill to just kind of get you used to doing this. So this r is just like f of theta. So if I want a set of parametric equations, I know that x equals r cosine theta, and y is going to equal to r sine theta. This is pretty much our go-to when dealing with polar function problems. So x of theta is going to be equal to sine of 2 theta is r. So that gives us the r value at any place. That's sine of 2 theta times cosine theta. And then y would then be equal to sine of 2 theta times sine theta. And that's it. That's all this problem wrote for us. So that would be your set of parametric equations right there. So we've gone from plugging in an angle, rotating to an angle, and then extending out to now having a situation where we can just plug in theta, get out an x value and a y value. Okay, all right, very, very cool. So now that was just a mini exercise getting into things. Now what we're going to do is we're going to integrate in the calculus. See what I did there? We're actually not going to do much integration. We're going to do differentiation. So the question first is, how do we find dy dx, right? And what is that? Well, dy dx is the slope of the tangent line, right? That's all that is. How do we find it? Well, let's go back to this step here. We're now having parametric equations, so it's not like polar's any different. In parametric equations, you take dy dt and divide it by dx dt. Here we're going to do the same thing, and it's going to be dy d theta, like so, and divide it by dx d theta. It's parametric. That's it. That still represents the rate at which we're changing in the y direction at some theta value, and the rate at which we're changing in the x direction, left and right, at some theta value. You divide up and down movement, rise, divided by run, and you get the slope of the tangent line at a point. That's it. So a couple of bits here. I said often we're going to want to find dx d theta or dy d theta. And remember, it still represents what I just mentioned, the change in the x direction or the change in the y direction at a certain instant, right? And that instant is going to be at a certain angle that we are at. So informally, basically, I like to think of it this way. Imagine any polar graph. Let's say it's a cardioid, right? Something like this. Oh, it's a good-looking cardioid. Not really. And so dx d theta gives you the velocity of the particle at a specific angle. So let's say we're out here at an angle like, I don't know, 5 pi over 6, and we're moving this way. So what that means is we got a tangent line going like that, but dx d theta, let's say, is negative. That means we're moving to the left. Dy d theta would mean that it would be negative in this case. We're moving down. That gives you the rate at which we're changing at this instant at a certain angle. That's it. That's all it is. So it's the same thing as we were doing in parametric. All right, let's keep cruising. So given r equals cosine theta on the interval 0 to pi, find the equation for the tangent line at theta equals pi over 3. This is going to become the same thing as a parametric equation problem. But first we need to make it into a parametric equation. or a set of parametric equations. So first we start with x equals r cosine theta and y equals r sine theta, and we'll build our parametric equations, and then from there it's old school. So r is equal to cosine theta, so I'm going to get x is equal to r, taking this and inserting it in for that value. That's cosine theta times cosine theta. Y is going to be equal to cosine theta, plug in for r, times sine theta. Nice. Okay, now from here, we're going to need to find the equation of the tangent line. So we need several things for that. Now, I am going to simplify this part down at least. That's cosine squared theta. This is just still cosine theta sine theta. Now to find the equation of the tangent line, as always, I'm going to put that right here. We need y minus y1 equals the slope times x minus x1. Now the order in which you find things doesn't matter, but we don't have the x or the y value, nor do we have the slope. I'm going to go after the slope first. To find the slope, we need dy d theta and we need dx d theta. So I'm going to find those independently here. Dx d theta is very simply the derivative of your x function, which we just found by converting everything in terms of theta. So dx d theta is the derivative of this. 2 times cosine theta, chain rule, times the derivative of the inside is minus sine theta. Now more on this in a little bit. Y, we're going to do dy d theta, and that's going to be the product rule. First d second, which is cosine theta, times derivative of sine theta is cosine theta, minus second d first. So that's sine theta. Oh, interesting. So that's going to be not minus, sorry, plus. How dare I say minus? So first d second plus second d first. So that's going to end up being a minus sine theta, the derivative of cosine being minus sine. Now we simplify this down, some interesting things happen here. We get minus 2 cosine theta sine theta. And over here, we get cosine squared theta minus sine squared theta. Now, it is perfectly fine to use these values as dy d theta and dx d theta. However, if you remember your trig identities, you might want to remember 2 of them for polar curves because they come up not too infrequently. The fact that sine of 2 theta is equal to 2 sine theta cosine theta. That's pretty helpful. And the fact that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So I'm going to use that in this particular problem. You don't have to though. All right, I want to be very clear. So that's cosine 2 theta here, and this is minus sine 2 theta. That's what they're equivalent to. So now if I want dy dx, remember dy dx is equal to dy d theta, so I'll write it like this, over dx d theta. Nice. So dy d theta is cosine of 2 theta. So we're going to evaluate that now, I should say, at the theta value that we want, pi over 3. So I'll put that here. Theta equals pi over 3. Theta equals pi over 3. Got a little excited there. And so we're going to do cosine of 2 times pi over 3. That's dy d theta at pi over 3. Then we're going to do minus sine of 2 times pi over 3. And I want to be very clear. You do not need to know these steps or those identities. You could have done cosine squared of pi over 3 minus sine squared of pi over 3 over minus 2 cosine pi over 3 sine of pi over 3. That will get you the same answer that we're going to get here. I just think that this is easier to do it this way if we can use those identities. You don't have to though. On the BC exam, you could leave your answer like that, but we'll simplify down. Cosine of 2 times pi over 3, or 2 pi over 3, is minus 1/2, divided by, this is negative, sine of 2 pi over 3 is root 3 over 2. And negative divided by negative is a positive. And so we're going to end up with 1/2 divided by root 3 over 2 is 1 over root 3. So now we've got y minus y1 equals 1 over root 3 times x minus x1. So now we need the x and y values. Where are we going to get those from? That's not so bad. I'm going to put that work up here. You have y equals cosine theta sine theta. So y of pi over 3, in other words, the y value when theta is pi over 3 is equal to cosine of pi over 3 times sine of pi over 3. And when we simplify that out, that's equal to 1/2 times root 3 over 2, or root 3 over 4. Nice. So that's going to be y minus root 3 over 4. That's our y value, equals our slope of 1 over root 3 times x minus. We need our x value. So x of pi over 3 is equal to cosine squared of pi over 3, which is the same as 1/2 squared, which is 1/4. And that's our final answer there for our x value. And there's our equation of our tangent line. So are there lots of little sub pieces that we need to do here? Yes, absolutely. We parameterize things first. That allows us to now treat it like a parametric equation. We need our x value and our y value at theta, so just plug in the theta value like we would in parametric equations if given a t value. Plug that in and get our values. I happen to then take derivatives and I do them and I use trig identities. You didn't have to. And then I'm plugging in pi over 3 into dy d theta and dx d theta to get our derivative by dividing them to get dy dx. Now, something very interesting here. So the point is at 1/4 root 3 over 4. So where's 1/4 root 3 over 4? I don't know. 1/4 is roughly here. Root 3 over 4 is, I don't know, roughly there-ish, I guess. Actually, 1/4 is going to be more like closer to here. Roughly there. I don't know. That's a rough estimate. So there's your equation of your tangent line. Now notice, this curve, when you plot it out, actually goes this way, which makes sense because dy d theta is negative 1/2. So we're going down, which makes sense. At this point, we're going down and to the left. That's it. So we're going down and to the left at that point. The slope of the tangent line, however, is positive 1 over root 3 because the slope is positive. That's because we're going left and down. Very interesting. I think that's very cool. Equation of the tangent line, put all the pieces together, and we're good. All right. So on to the next little part now. So we can now use the information that we just found to find horizontal as well as vertical tangent lines. So let's go back to that old concept. Just like in parametrics, because this is basically parametric, if I want the value or values of theta on this interval at which the curve has horizontal tangent lines, remember, that goes like this. That means dx d theta is not 0, but dy d theta is 0. To have a horizontal tangent line, that means you're not moving up or down. I'll say and dx d theta does not equal 0. All right, so I'm going to go back to our derivatives. dy d theta we found over here was cosine of 2 theta, essentially. And this is where actually simplifying it becomes very important, right? So we have that dy d theta was cosine of 2 theta. And again, we found that. It's the exact same equation. So I set that equal to 0. dx d theta, which we're going to need to know, was minus sine of 2 theta. So that's minus sine of 2 theta. All right. Now that, again, is dx d theta. So to solve for this from 0 to pi, I set 2 theta equal to the places on the unit circle where cosine is equal to 0. And where's cosine equal to 0? Well, that would be here at pi over 2 and here at 3 pi over 2. Be pi over 2, 3 pi over 2. And you don't want any values greater than that because 5 pi over 2, when divided by 2, would be 5 pi over 4, which is greater than pi. So this gives us everything we need. We divide both sides by 2. That'd be pi over 4 and 3 pi over 4. Now, we need to test. These are not necessarily the values that work unless we don't get 0 here. So I'm going to check and say that negative sine of 2 times pi over 4, that's actually going to equal to negative 1, which doesn't equal 0. And we've got negative sine of 2 times 3 pi over 4. So I'm checking the theta values here to make sure that we don't equal 0 in the x direction. Well, that equals to negative sine of 3 pi over 2, or it ends up equaling positive 1, which doesn't equal 0. Okay, so dx d theta doesn't equal 0 at the places where dy d theta does equal 0. So therefore, these are our solutions, which makes a lot of sense because here's pi over 4. The circle's moving this way, so as we move that way, check it out, dx d theta is negative. So we're moving to the left, and we have that horizontal tangent line. Then we circle all the way around. This ends up being down here at 3 pi over 4. Remember, that's because we reflected 3 pi over 4 over down to here. And notice that dx d theta is positive there, which makes sense because we're moving to the right at that instant. Isn't that awesome? I think so too. All right, we got one more problem, and that's going to be vertical tangent lines. And then that'll basically complete not just a crash course, but a really nice understanding of all of this motion on a polar curve. All right, so find the value or values of theta at which the curve has vertical tangent lines. So here conceptually, to have a vertical tangent line, dx d theta should not equal or should equal 0. But dy d theta, That should not equal to 0 because we want to be able to move up and down, just not left and right. That's what a vertical line would look like. So dx d theta, I'm going to take that from the last slide there. Dx d theta is minus sine 2 theta. So that's minus sine 2 theta. Very nice. So that's minus sine 2 theta. And then we've got right here, let's see, dy d theta. And dy d theta was cosine of 2 theta. So we want that not to equal 0. We want this to equal 0. We're going to look at the unit circle again. Here we go. Oh, yeah. I don't know why I'm talking like that. I'm just excited. It's fun. So this is going to be where sine is 0. Sine is 0 at 0 and at pi. And then again at 2 pi. And I think that'll do it for us because we've got 2 theta, that's the angle, is equal to 0, pi, and 2 pi. And if we go up any higher, even if we divide by 2, we're going to get numbers above pi, which is outside of our interval. So we divide by 2, I get theta equals 0 over 2 is 0, pi over 2, 2 pi over 2 is pi. So now let's check it out. We want to make sure that this does not equal 0 at any of those values. So cosine 2 times 0 equals 1, which does not equal 0. So that's dy d theta there. We've got that cosine of 2 times pi over 2, that equals to negative 1. It's cosine of pi, which doesn't equal 0. And then back again to cosine of, let me do this here, 2 times pi, which is equal to 1, which does not equal to 0. So we're good there, except it says find all the values of theta at which the curve has vertical tangent lines. It does say on that interval, so I am going to technically include pi, but it depends on what your teacher asks you for. If your teacher's saying, but don't have any repeat points, then you should actually not include pi. Let me show you what I mean. At 0, we're right here, which makes sense because we got a vertical tangent line, and lo and behold, since the curve goes that motion, we're moving upwards. Dy d theta is positive. Nice. Then as we rotate around, that gets us to pi over 2, and we get this vertical tangent line where we're moving downwards. Dy d theta was negative right there. Dx d theta is 0, another vertical tangent line. As we swoop back over, we get to the same exact point again. So pi is technically on the interval, but it is a repeated point. So it depends on what your teacher's looking for. If they're looking for all theta values on that interval, then we got them. If they're just looking for non-repeating locations, then it would just be 0 and pi over 2. All right, that's it. In the next video, we're going to talk about some awesome stuff with dr d theta. So we're going to drop the whole parametric thing and see what happens there. But for now, bask in the glow that is basically parametric equations mixed with polar equations. It's awesome. Peace.